Hi everyone, so now we're going to go ahead and do these examples on the property of limits note. So we're going to go through and actually find a whole bunch of limits using these different techniques. Okay, it's really fun. I actually really enjoy doing this. I know you're going to make fun of me, but oh well. This is why I love teaching math. I get to do stuff like this every day. Woohoo! So in all of these examples, we're going to find limits where we cannot just use direct substitution. So we can't plug and chug because we get the indeterminate case if we try to do that. So remember, the indeterminate case is when you get 0 over 0, or a whole when you try to evaluate a limit. So notice that if you put 3 into this function, you would get 0 out of 0. So how we find limits, there's a bunch of different techniques, and I basically have one example per technique to outline for you. And then it's just your job to identify when to use each technique. So notice that this numerator is factorable, so we're going to factor it. Okay, so we think what multiplies to -3 and adds to -2, so that's x minus 3. Oh, and see, I just did the bad thing. That is really tempting to do. Don't do it. I forgot to include my limit statement every time. So when you're finding limits, it's super annoying, but you have to include this as part of your calculations. Okay, so the limit as x approaches 3 of x minus 3 bracket x plus 1 all over x minus 3. So notice now this crosses off. So you get the limit as x approaches 3 of x plus 1. So now you have a continuous function, and so now you can actually use direct substitution, substitute in 3, so you get 4. So this means that this function, as x gets closer and closer to 3 from either direction, this function is getting closer and closer to the value of 4. Okay, now we have this type of limit that involves a root. Okay, so when you see anything with a square root, that is the indeterminate case, you should think about rationalizing. So either rationalizing the denominator or rationalizing the numerator. In this case, our square root is in the numerator, so that's what we're going to rationalize. So if you remember, when you have a 2-term like that, we multiply by the conjugate. So in this case, the conjugate is root x plus 1 plus 1. And then we also divide that again, so that in essence, we are actually just multiplying this function by 1. And that's why we're allowed to do that. But by multiplying by a conjugate, we're able to simplify this in a way that is useful to us. So we include our limit statement. So the limit as x approaches 0. So root x times 1 times root x plus 1 is just x plus 1. And then the middle things cancel out. That's the whole point of doing the conjugate. And then minus 1 times minus 1 is minus 1. And then the denominator, there's no need to actually simplify it. You can just keep it as, you'll see why. There we go. So now notice that when we simplify this, you get x plus 1 minus 1. So you get, these ones will cross off, okay? And then you get this x and this x, which also cross off, okay? Because you get just x on the numerator, and then that will reduce with this x. So you're actually just left with 1 over root x plus 1 and then plus 1. So notice now this is no longer the indeterminate case. So now we can plug and chug and actually just substitute in 0. So you get 1 over root 0 plus 1, which gives us 1 over 2, because root 1 is 1, 1 plus 1 is 2. So notice where I'm able to drop the limit statement. It's when I'm actually evaluating the limit. So when you're actually putting 0 into the function, that's when you don't need to write the limit statement anymore. Okay, so that's rationalizing. So here we have another example where I'm going to use something called the substitution method. So this one you could try rationalizing the denominator and that would work, but I'm going to use substitution to show you a simple substitution because later we have a more complicated substitution method. So I am going to say, I'm going to let, on the side here, I'm going to let the root of x be equal to u. Okay, so I'm going to substitute this root x with u. So because that root x is in terms of u, anything involving an x needs to be in terms of u. So I also need to represent this x in terms of u. So if root x is u, then x is u squared. Okay, because I'm squaring both sides. And if this is true, then as x approaches 1, then what is, so as x gets closer and closer to 1, what does u approach? Well, in this case, u would approach 1 as well. If x is 1, then u is 1. So now I can replace all of my x's with u's. So I'm going to say that this is the limit as u approaches 1 of u squared minus 1 divided by u minus 1. So now we'll see why this is more useful. So the top here, the numerator, is actually a difference of squares, so we can factor it to be u plus 1, u minus 1, all over u minus 1. Okay, so now these cross off, and we are actually left with the limit as u approaches 1 of u plus 1. Okay, and then often I use this notation where, so now I'm just letting this go to 1 just to show that I'm plugging and chugging. Okay, and then so you get the response of 2, the answer of 2. All right, so that's how to use the substitution method. So let's do it again with a more difficult example here. All right, so what is it that's really gross in this question? Well, obviously this x plus 8 to the 1/3. So I'm going to let the whole thing, x plus 8 to the 1/3, that whole thing be equal to u. So I'm going to replace that with u. So now we have to figure out how are we going to replace this x and how are we going to replace this limit statement here, the x approaches 0. So we need to solve for x in terms of u. Okay, so we get x plus 8 equals u to the 3. So x equals u to the 3 minus 8. So that's how we're going to replace x. So now we have to think about our limit statement. So as x approaches 0, which is what we have here, what does u approach? Okay, so look here. As x approaches 0, we would have 8 to the 1/3, and 8 to the power 1/3 is 2. So u approaches 2. So now we're going to replace this entire statement with u's. So we have the limit as u approaches 2, not 0, of u. So this whole thing, we're just writing u instead, minus 2. And instead of x, we're writing u to the power of 3 minus 8. So how does this help us? Well, now we have a difference of cubes in the denominator. And we know from advanced functions how to factor a difference of cubes. So that would be u minus 2, okay, because 8 is just u cubed, so u minus 2. And then we have u squared plus 2u, okay, so the factors multiplied together, and then plus 4, so the cube root of this squared. Okay, so oopsie, these cross off, and then after those cross off, well, I'll rewrite it. You get the limit as u approaches 2 of 1 over u squared plus 2u plus 4. Okay, and now you're able to just substitute in 2. So this goes to 2 squared, this goes to 2. So your solution then is 1 over 12, because you get 1 over 4 plus 4 plus 4, so 1 over 12. So this function, as x approaches 0 from either side, the function approaches a y value of 1 over 12. Okay, our next example here involves an absolute value. So anytime you see an absolute value, I want you guys to think about doing one-sided limits. Okay, because an absolute value changes something from positive to negative depending on where you are. So you need to use one-sided limits to see what the function is approaching from either side. If the function approaches the same thing, then that is the limit. If the function approaches two different real numbers, then the limit does not exist. So anytime you see an absolute value sign, think one-sided limits. Okay, so think about this. So this function can be rewritten as x minus 2 divided by x minus 2 if x is greater than 2. Okay, because if x is greater than 2, then the numerator is just a positive number and nothing changes. Okay, however, what happens if x is less than 2? Well, the denominator is still x minus 2, but the numerator would be negative and the absolute values make it positive. So you would negative that negative to make it positive. So this actually just means, check this out, this x minus 2 over x minus 2 is really just the constant 1. So if x is greater than 2, this function is just equal to 1. However, this is negative 1. So really this function is just equal to a horizontal line at negative 1 for all values less than 2. That's very interesting. In fact, we should include, oh sorry, we can't include 2 for this because then you would get the indeterminate case 0 over 0. So let's take a look at this. So the limit as x approaches 2 from the negative side of f at x is negative 1. Okay, as x gets closer and closer to 2, but being less than 2, you actually get closer and closer to the value of negative 1. But the limit as x approaches 2 from the right of f at x is equal to 1. Okay, so what does that tell you? It tells you that the limit does not exist. So the limit as x approaches 2 of f at x does not exist since these two one-sided limits are different from each other. If you want to visualize what this function looks like, there's your axis. Honestly, it's just, here's your x value of 2. So you would have an open dot here and going this way at 1. And this is negative 1. You would have an open dot here going this way. That's what it would look like. So the limit does not exist. All right, one more example. Okay, so we're in this function, we have root 9 minus x squared. So again, we're going to find the two-sided limits because we're not really sure what to do with this. So when in doubt, you can always do two-sided limits and see what happens by throwing in some values. So let's think about this in that way. So the limit as x approaches 3 from the left of f at x. So think about what kind of values those would be. Sorry, I'm just looking at my notes. So as x gets closer and closer to 3, so let's put in like 2.9. So 2.9 squared is almost 0. It's almost 3 squared. So you're getting closer and closer to 9 minus 9, and the square root of that is just 0. So the closer and closer you get to 3 from the left, so 2.9, 2.999, 2.9999, this function is getting closer and closer to 0. And you might be saying, well, Mrs. Weeds, can't I just plug and chug because this is a continuous function at 0? No, like, can't I just throw it in? Well, look what happens on the other side of the limit. The limit as x approaches 3 from the right of f at x. So again, just consider these values. 3.1. 3.1 squared is greater than 9. We know that for sure. So 9 minus something greater than 9 will give us a negative number. Uh-oh, that's a problem. We can't take the square root of a negative number. So this actually is not defined. The function, in fact, does not approach 3 from the right-hand side. It kind of ends at 3. So this means, interestingly enough, that the limit as x approaches 3 of f at x does not exist. Even though the function is defined at 3, the limit does not exist at 3. Okay, so if you remember what this looks like, this is actually a half circle. So here's -3, here's 3, super rough. Sketcheroo for you guys. So this is what this function looks like, a half circle. So even though the function is defined there, it does not actually get approached at all from the right. So therefore it doesn't exist. Okay, so again, I gave you kind of one example of each of the different types of limits and how when the indeterminate case happens. So hopefully that's enough to get you guys going and get started on all the questions, and you can practice so you can get really good at doing this on your own. And it's fun working with algebra this way and getting to the right answer. So thanks for watching, guys. Hope you learned lots.